Okay, so in this session we will start talking about how we can make how the agent makes decisions, right? So at every point in time, the agent needs to take a decision on what is the next action that needs to be taken. So how does it make these decisions? So that's what we are going to talk about in the next 2-3 sessions. So when we talk about decision theory, it deals with choosing among actions. So we have a number of actions which are possible. So how do you choose among these actions, okay, on the desirability of the immediate outcomes, okay? So suppose you take an action A and we say result of A, okay, which tells you what is the outcome state. So it's a random variable which tells you what is the outcome state which results from taking action A. Then the probability of getting an outcome S, okay, given evidence C, you can write as probability of result of A is equal to S given A and E. Okay. So whatever A we have here is the action A, is the event of action A being executed basically. And the agent's preferences are captured by what is called the utility function, which is called U of S. Okay, so the utility at for a particular state S. Okay. So now the expected utility of an action, okay, given the evidence is expect EU A given E. Okay, it's the average utility value of all the outcomes that you can get. So expected utility of action A given evidence C will be equal to sigma of P result of A is equal to S dash, where S dash gives you a particular outcome. So we are talking about a summation over all the outcomes that are possible given A and evidence C into U of S dash, right. So this that's a utility of S dash. So this is called the expected utility. So this expected utility is for a particular action. So now if you see what is the expected utility of all the actions and then choose the action which gives you the highest expected utility, okay, that is called maximum expected utility, that is MEU, okay. So that is the action to be taken. So the action will be R max of A EU action A given evidence. So the agent does the right thing, so which is the rational thing to do, okay. So now estimating the state of the world or whatever we are trying to do over here, right, we are giving it in the form of variables, but then how does the agent get all these values? So estimating the state of the world requires perception, learning, knowledge representation and inference. And computing probability result of A given A evidence requires a complete causal model of the world and NP hard inference in Bayesian networks. We just saw Bayesian networks, right? So it's not really that everything is that easy, right? We need to get all these values from the agent has to get all these values, and finding the utilities requires searching or planning. So what we are saying is that if you use the MEU principle or the maximum expected utility principle, okay, it's equivalent to saying that you have a performance metric, okay, over the environment, and you are trying to see that that performance metric is maximized. Okay, now for a agent to take a particular decision, it has to make a decision on what its preference is, right? And we can see that when it comes to utility, it depends on preference. Okay, it prefers a particular A to some B, or state A to state B, or action A to action B, etc. Right? So let us see something about what preferences are. Okay. So basically, sometimes you can take a decision by just knowing the preferences. You don't need to know the exact values of some variables. So when we say that, when we say A is, when the agent A, when the agent prefers A over B, right? You denote it in this way, and if when you denote in this way, it means that the agent is indifferent between A and B. Okay, it doesn't mind whether it chooses A or it chooses B, and this shows that the agent prefers A over B, or it is indifferent between them. Okay, so this is some notation that we are basically talking about. So now, if we look at an action that is being, you are going to get a set of outcomes, right? And each of these outcomes will have a probability which is associated with it. Okay, so we can look at this for every action. If you look at the entire set of outcomes along with the probabilities of each of them, it is known as a lottery, right? So a lottery L with suppose you have the outcomes S1 to Sn, okay, and they occur with probabilities P1 to Pn. Okay, in other words, S1 occurs with probability P1, S2 occurs with probability P2, etc. Then we can write the lottery in this way. So that is P1 S1, P2 S2, etc. So this is a way you write a lottery. So it's also possible that the outcome, a particular outcome which we are talking about here, may be an atomic state, or it could be another lottery that you are talking about, right? So when you talk about preferences, there are some constraints that it follows. One is what is called orderability, okay, which means that if you have two lotteries, okay, A and B, then the rational agent has to choose one of the preferences that are available. Okay, like it cannot say that I don't know. Okay, in other words, exactly one of A is preferred over B, or B is preferred over A, or it does not have any preference, right? So one of these three has to be true. So that is the first one. Second one is what is called transitivity. So if A is preferred over B and B is preferred over C, it implies that A is preferred over C. And third one is the continuity. So when you say A is preferred over B and B is preferred over C, then there exists some probability P such that if you take that probability A and 1 minus P, probability C as the lottery, okay, and if you consider taking B instead of this, okay, it's indifferent about taking either this or this for some probability P, okay. So that is the continuity. Next one is what is called the substitutability, okay. If the agent A is indifferent between A and B, then the agent is indifferent between two more complex lotteries that are the same except that B is substituted for A. So if you take one lottery where probability of A is P and 1 minus P C, it's, and if you replace that A by B, right, then the agent is indifferent between these two. So that is called substitutability. Next is monotonicity. If you have two lotteries, okay, with the same two possible outcomes A and B, if a agent prefers A to B, then the agent must prefer the lottery that has a higher probability for A. Okay, so this is one lottery. So here you have A with probability P and probability 1 minus P. You have another a lottery here, okay, QB and 1 minus PC. So this will be equivalent to having a lottery with A, B and C in this way. So this you can see here in this figure. So you have A and B, and this one is a complex lottery. So you have Q and 1 minus Q over here. So this is equivalent to saying this has probability P, this has probability 1 minus P, and this has probability y minus P into 1 minus Q basically. The next is what is called decomposability. Okay, compound lotteries can be reduced to simpler ones using the laws of probability. Okay. So this is exactly what we saw here, right? So this complex lottery can be decomposed into the simpler one. That is a decomposability axiom basically. So you know, you need to have an agent that is rational. Okay, so so an agent has to follow all these whatever we said over here, right? All these 6 constraints. If it doesn't follow these constraints, then it will lead to some irrational behavior. For example, if you say the agent prefers A to B and B to C and C to A, right? So this will be equivalent to this thing over here, right? So this is actually non-transitive basically, and this leads to irrational behavior. Okay, this is not basically possible. Okay, so it has been shown here that you know, if agent A currently has A, then we could offer to trade C for A, okay, and plus 1 cent. The agent prefers C and so it would be willing to make this trade. We could then offer to trade B for C, extracting another cent, and finally trade A for B. So what do? We come back to the starting point and the agent has given us 3 cents, right? And you can keep going through the same procedure again and again till the agent has no money. So this actually is irrational behavior basically. So this is not really done. Okay. Okay, so now we have talked about what do you mean by preferences. So we need to see the utility. So what we basically want is that we don't want exact utilities or anything. We just want the utilities to reflect the preferences that are being made. Okay. So suppose you take utility functions. Okay, you have 2 values A and B. So utility of A, if utility of A is greater than utility of B, this is only possible if the agent prefers A over B. So utility of A is greater than utility of B if and only if A is preferred over B. And similarly, utility of A is equal to utility of B if and only if it is indifferent to whether it chooses A or B. Okay. And what is the utility of a lottery? Utility of a lottery is the sum of the probabilities of each outcome times the utility of that outcome. So suppose we have a lottery like this, P1 S1, Pn Sn. We can say it's equal to sigma Pi utility of Si, right? So this is the utility of this particular lottery that we are talking about. So then you can choose a action that maximizes the expected utility, right? So it doesn't have to be unique, like they say the utility doesn't have to be unique. You could also transform all the utility functions by saying A times utility plus B, right? And it doesn't matter because it's only a preference. Okay, so it goes according to the preference. So it is completely general basically. So what you have is something like a preference ranking on the states. The numbers really don't matter. So this is called a value function or a ordinal utility function. Okay. Okay, so let us look at what you mean by utility functions. Okay, utility is a function that maps from lotteries to real numbers, right? So we just saw how you can take a lottery and convert it into a utility basically. Okay. But what happens is that the preferences can be sometimes not really rational. Okay, so for example, an agent might prefer to have a prime number of dollars in its bank account. Okay, so if it has $16, it would give away $3, right? So that is not a rational behavior. Okay, also the agent may prefer a dented 1973 car to a shiny new Mercedes, right? So you can't really say what would be the preferences. Okay, the preferences of people you find are also sometimes very unusual. What you see. Okay, so we need to work on what is the agent's utility function. Okay, so we don't know what the utility function is. So generally, it's known as preference elicitation. How do you find the utility functions? Okay, so in other words, you are trying to see what are the preferences of the agent, which leads to the utility, basically. So generally what is done is you need to have a scale for these utilities. So what has been fixed is something between 0 and 1. Okay. So suppose we say that the utility of the best possible price, okay, is US is equal to U into this value, and the worst possible is this one, right? So we could say that what we want is that utility scale should be between this ut and u inverted t, right? So it needs to choose between S and a standard lottery in this way, P u t and 1 minus P into u inverted t. In other words, this could be the best and the worst, okay, and S will be between these two, right, basically. So if you take this worst possible, okay, it will be the value which will assign to the worst possible calamities that can happen, for example immediate death or etc., right. So what is done is that they do put a monetary value on life, right. We need to see how they do that, right. So this is somewhat by the side, because they talk about how people, the value that people place on their own lives. Okay, so for that they use what is called the micro mart. Okay, this is one of the currencies that is used in medical and safety analysis. So micromart, if you look at micromart, driving in a car, okay, for example, driving in a car for 230 miles incurs a risk of 1 micromart. Over the life of your car, say 92,000 miles, that's 400 micromarts. So in other words, you are putting some value on your life. So what is a micromort? Micromort is 1 in a million chance of death, right? So that is what is used over there. You also have another measure called quality adjusted life year, okay. So for example, if you have a patient with disability, they are willing to accept a shorter life expectancy to be restored to full health, right? Or if a kidney patient are indifferent between living 2 years on a dialysis machine and 1 year at full health, right? So this is what is used in the quality adjusted life years. Okay, so you are ready to give up some of your life years, right, to get a better quality of life. Okay, so let us look at the utility of money. right? So economics actually provides a lot of information on utility theory basically. Okay, so the agent exhibits a monotonic preference for more money. So we can say that um, the if there is more money, it has higher utility, right? And if there is less money, it's got less utility. Okay. Now, so suppose you're given this choice. Okay, either you make this 10 lakh dollars according to our Indian thing, 1 million prize. Okay, or if you flip a coin, if it comes up heads, you end up with nothing, and if it comes up tails, you get $2.5 million, right? So would you take that up? Okay. Most people don't take this up. Okay, they just pocket the million, right? So how do you assess this actually? You look at what is called the expected monetary value. Okay. So the expected monetary value of the gamble is half into $0 and half into 2.5 million. So you get 1.25 million, which is more than the original 1 million. Okay, but you cannot take a decision on this. Okay, I don't think. What you are doing here is basically people like to be sure. Okay, they don't want to go in for probabilities, etc. Okay. So suppose SN denotes the state of possessing wealth N, right? Then you could write the expected utility of accepting it will be half U of S of K, right? Where K is the value that you have, your current wealth is K, right? Plus half utility of S of K plus 2.5 million. And EU decline will be utility of S of K plus 1 million, right? So this is one way of writing the expected utility of whether you accept or you decline. So the utility that you assign, okay, to your current financial status, suppose you say 5, a 9 to this one and a 8 to this particular state, then the rational action would be to decline, because the expected utility of accepting is only 7. Okay. But then it depends, if it is a billionaire who already has a lot of money, he may want to go in for the gamble, right? So we can't say what you mean by rationality. Many people have different ways of saying what rationality basically is. Okay. So one way of utility functions, the utility of money, is by taking the logarithm of the amount. Okay. So it's like this, you get a curve like this. Okay. So in this limited range, right, what would be the utility of the money is what is given here, and it's like a concave curve. So you find that most people go in for this type of a concave curve. Okay, but it depends on the range in which you are working. If you are in the end parts of this curve, okay, if you in the end parts, the behavior will actually change. The behavior doesn't remain the same. So what happens is the agents with the curves of this shape, like we saw here, this concave curve, okay, they are actually what are called the risk averse. Okay, they prefer a sure thing with a payoff that is less than the expected money of the gamble. Okay, but suppose somebody is in the desperate region, they don't have anything. Okay, they have a large negative wealth maybe. Okay, then they may have a behavior which is risk seeking, right? So it depends on that. So certainty equivalent, the value an agent will accept in lieu of a lottery, okay, is called the certainty equivalent of the lottery. And the difference between the EMV and the of a lottery and its certainty equivalent is called the insurance premium. For small changes in wealth relative to the current wealth, almost any curve will be approximately linear, okay. And an agent that has a linear curve is said to be risk neutral, okay. It's neither risk seeking nor is it risk averse, but it is risk neutral. So this is true for gambles with small sums basically, okay. So the rational way to choose the best action is this one, right? You take expected utility and choose the action. We just saw that right at the beginning, right? So that is the best way to choose the right action actually, okay. So what happens is that, okay, you make that estimate EU, but EU may not be exactly correct, right? So we are working with the estimate EU, which is given in this way, okay. So if you take the difference between the estimated expected utility and the actual expected utility, okay, you want this to be 0, okay, that's the thing. So this difference, so what happens is that you make an estimate but it may not actually be correct, right? So when that happens, then you need to find the difference between this and see what is the error, right? And the expected value of error, this gives you the expected value of error, and you want this expected value of error to be as less as possible. Okay, so how does this actually affect? Okay, so you may have things like serious manifestations include believing that an exciting new drug has cured 80% of patients in a trial and will cure 80% of actual patients. It may not really happen, right? It may be the case what appears to be the best choice may not be. So a drug selected from thousands tried that has cured 9 of 10 patients is probably worse than one that has cured 800 out of 1000, right? So it depends on the choice that you actually make for the utilities, right? So this is known as the optimizer's curse basically, right? And we can avoid this by using an explicit probability model, probability of EU estimated given EU of the error, okay, and using that. Okay, so if we look at these choices of lotteries A and B and C and D, okay, A has 80% chance of getting $4,000 and B has 100% chance of getting $3,000 and C is 20% chance of getting $4,000 and 25% chance of getting $3,000. So people generally prefer B over A and C over D basically, okay. So, so we can see basically that people sometimes prefer irrational preferences, right? So this is what is called the certainty effect. People are strongly attracted to gains that are certain. Okay, so you are definitely going to get that. Okay. So for example, if people know that they would experience regret if they gave up a certain award B for a 80% chance at a higher reward and then lost, okay. So people who choose B over A and C over D are not being irrational, okay. They just don't want to lose and then feel okay, we made the wrong decision basically, okay. Similarly, you have another here where You get $100 for a red ball and $100 for a black ball, $100 for red or yellow ball and $100 for a black or yellow ball. But what you have is the urn contains 1/3 red balls and 2/3 either black or yellow balls, right? So here you have ambiguity aversion. Okay, so wherever there is ambiguity, they don't want to get into that. Okay, A gives you a 1/3 chance of winning, while B could be anywhere between 0 and 2/3. So because ambiguity is there, they prefer to go for the other one. Another problem is the exact wording of the decision problem, which is called the framing effect. For example, if you say something like 90% survival rate, people find it easier to accept that. Instead of having 10% death rate, even though you can say both the statements are the same. Okay. So what they do is, for example, in a restaurant, they will offer a $200 bottle wine which no one will buy. But then why they do that is so that if a customer takes something at $55 and he thinks that it's a bargain that he is getting, even though it may not really be a bargain. So this is what is known as the anchoring effect basically. Okay, so the wording etc. is important. Okay, so we'll stop at this point and we'll talk about the multi-attribute utility function in the next session basically.